Hello everyone, this is Dr. Young, and in this video we're going to talk about atomic absorption spectroscopy and atomic emission spectroscopy. You know, how are they similar, how are they different, what are they used for, and then partially how it leads us along this story, right, from not having any idea what the electronic structure of an atom is to getting to sort of these quantum numbers, this idea of orbitals. So I remember that in the past videos, we talked about how light has particle and wave-like properties like interference and diffraction. This video is going to be all about this stuff, right? So what's going on with this absorption and emission spectra, and why, what's going on with this specific wavelengths of light. So I kind of want to show you what that's all about. Now, right, remember from the previous video that light's a photon. It has wave-like properties and particle properties. Particle-like in that it can travel through a vacuum, which waves can't. And wave-like in that it's massless and that it interferes and that there's this thing called diffraction. And the diffraction is the thing that I'm going to focus a lot on in this video, right? Remember that diffraction is when you have white lights, right? This is supposed to be white light coming in, which is supposed to be all the wavelengths put together. You put it through a prism, and then diffraction is the idea of the light speed will change as it moves through a different medium, and when it changes like this, you can spread out that white light because the different wavelengths of light travel at different rates through different media, and then you get yourself a little rainbow. Right, you get all the way from your violets to your reds. You get this whole spectrum, right? This would be called the full spectrum of visible light. Another thing to kind of keep in mind, another term that you might hear, so this is the full spectrum of light. You could also call this actually is also called a continuous spectrum. Because you'll notice that as you look through this, there are no breaks in it. It just goes from one color to the other one, all nice and pretty like, right? There are no breaks in it, and I'll talk about those breaks here in a second. So it's long been observed, people learned that if you put different elements in a fire, that different color flames formed. And it's really cool. Can you imagine being like one of the first people who threw a random rock in a fire pit and all of a sudden it turns green or red or something like that? This is like total magic stuff. And you can see here, I don't want to mess with this too much, but you can see on the left you have things like indium or cesium are kind of these purpley colors. You move into the middle, you've got this boron and copper are kind of these greenish flames, and then orange from sodium and red from things like lithium and strontium. Now, these colors are also kind of, as a side note, what makes fireworks their colors, right? So when you look at the 4th of July, people shoot off fireworks, those colors are from the different elements that they're put in those fireworks, right? So if you want a red firework, you might throw in strontium, for example. If you want a green firework, you might throw in some copper. But these flames, right, have different colors. So people start to think, well, that's super cool. Well, what if we put them through prisms? And that's kind of how that's how this emission spectroscopy sort of forms. So let me kind of show you what that's all about. So we have two types of atomic spectroscopy. There's atomic emission spectroscopy, which I'm going to talk about right now, and then there's atomic absorption spectroscopy. So emission just means that light is being emitted from something, right? So if I look over here, this would be like the flame test type of idea. So this is like a flame test where the idea is that you just get a little bit of a compound on a wire or something like that, and you put it in a flame and see what color the flame turns. So it'd be like a flame test, but the idea is that light is going to be emitted from this sample, right? So light is emitted from the sample. Right? It's coming from a source. The element, the hot element, is that source. So the idea here is that light goes through, comes from the compound being heated up in a flame, goes through a slit to kind of focus it, and then you just put it through a prism and you see what light is coming out of it, right? And at first, right, it might seem like, oh, well, all of the orange, right? If sodium looks orange, maybe it's just this orange chunk of the spectrum is going through, right? And so I have the full spectrum up here, but it looked like it wasn't really just like that orange chunk, right? The idea is that it was two like lines. It was just like two parts. It wasn't the whole thing, right? There's just two lines here, specifically at 589.0 nanometers and 589.6 nanometers, right? As you can see, these two very specific lines. And that was kind of bizarre because you'd think it'd just be, again, just that orange chunk, but it wasn't. It was very specific lines. And it turns out that if you do this with different elements, you get these very specific lines that are emitted when you heat up these different elements. And so you get what are called these emission spectra. And these spectra are unique for each of the different elements, right? They're sort of like fingerprints for these atoms. And so like helium, right? I've got the one up here for helium. Apparently it only has 1, 2, 3, 4 wavelengths of light that get emitted from it when it heats up. Ditto helium, like it has all of these. Here's one for lithium, beryllium. I only put these 4, but you can do this for basically any of the other, any element that can be heated up and it'll emit, whether it's all the way up to uranium. And this is all, so the idea is that all helium samples look like this. It's not like mine will look different than yours. All of them look the same. Now, the opposite of atomic absorption spectroscopy is where, oh, it's not a sample is burned. I'm sorry, let me fix this up. Absorption is that light goes through a sample. So light, the full spectrum, passes through a sample. Now the idea here is that some of the light gets absorbed. Hence the term absorption spectroscopy, right? So here down here you have a source of white light, that's the full spectrum. It goes through a sample, and the idea is that not all of the light goes through here, right? So that well, let me show you. Right, it'd be like, imagine that you have a photon of a wavelength that looks red, you have a photon of a wavelength that looks green, and you have a photon of a wavelength that looks blue, for example. And the idea is that if it passes through the sample, maybe the green one gets absorbed. So now only the red and the blue go through. And so then that light would go through the slit, only the blue and red. And it would go through a prism, and you look on the screen, and what you'd see is you'd see the full spectrum, but minus whatever light was absorbed by your sample, right? So you'll see these black lines now. So it's the full spectrum. You see the full rainbow, but you'll see little black lines where that sample, whatever that element was, absorbed light, right? And again, so here's the one for hydrogen, here's the one for helium, here's one for neon. You can see that neon, right, has a whole bunch more. It almost looks like a barcode on your food or something like that, right? It almost looks like a barcode. It has all of these different places where it absorbs light, and it's very specific, right? We can say that it's at 600 nanometers or 575 nanometers or 680 nanometers or something like that. We can quantify what light gets absorbed. And what we see is that the absorption spectroscopy is the exact opposite of the emission spectra, right? So the absorption spectra is the opposite of the emission spectra, and I'll show you that in a second. But here are some more examples of unique spectra obtained. They're fingerprints of the atoms. This is just the opposite, right? So here's your hydrogen. It's got 1, 2, 3, 4 lines, right? So if you shine the full spectrum through hydrogen, it absorbs here, it absorbs here, and it absorbs here and here. Same thing for helium, lithium, beryllium. Again, they all look different, right? So if I had some unknown substance, I could shine light through it, see where it absorbs, and I'd be like, oh, hey, look, it's absorbing right here and right here and right here and all of these spots. That must be helium. I can match an unknown to these very well-known spectra that are obtained from either emission or absorption spectroscopy. Like I mentioned before, right, they're the same but opposite lines. So if you have a hydrogen emission, right, remember I said it's 1, 2, 3, 4 lines that get emitted when you heat up the hydrogen? Those are the exact same spots. If you look here closely, those are the exact same spots that are absorbed when you do the absorption spectrum, when you find the absorption spectrum for hydrogen. And it's the same thing for all of the elements. The absorption and emission spectra look the same for lithium. They look the same for sodium. They look the same for helium. They're the same but opposites. So for some reason, when you shine light through a thing or you heat it up so it emits light, there are these certain wavelengths of light that apparently are really important and really unique to that atom. And that was really interesting to people. And that's why they wanted to explore this more, because they thought that it might have something to do with electrons. And that's what kind of gave us the Bohr model, which I'll talk more about in a sec. Now, in general, why is this useful? Like I was mentioned before, you can identify unknowns. If you had some weird gas and you're like, well, what is this? Or some substance, you can use atomic absorption spectroscopy to figure out what it is, because you can just match it to a database and be like, oh, apparently that's helium and carbon and whatever. It's used in environmental science to, for example, look at a water sample. You can shine light through it and see like, oh, hey, there's this metal and that metal and this metal in it. Maybe you don't want to have lead in your drinking water, for example, if you're in Flint, Michigan, right? Maybe you don't want to have a whole bunch of like chromium floating down your river that's a water source for a town that was emitted by some plants, polluting that river. You can test for these metals, for these substances, using atomic emission or atomic absorption spectroscopy. Also, things like if you're mining, people can like take the like wastewater from mines and stuff and test that and be like, oh look, there's silver, there's gold, there's copper, there's whatever in my samples. Because again, all those elements have their own fingerprint, their own very specific spectra. One of my favorite uses is in astronomy, right? When you hear people say like, oh, there's a nebula and it's got helium and blah, blah, blah gas, or this planet is made out of that, or we found this this planet out here is mostly made out of iron also, or all of that is information that is taken from spectroscopy, from this atomic spectroscopy. The light that comes from a star or bounces off of a planet or something like that. The idea is that the elements in that absorb or emit light based on what atoms are in there, what types of elements are in there. And so that's how we can find out from, we've never been to a certain planet, but we can be like, oh, look at the light that's coming from it. It has gaps here, here, and here. That must mean that there's carbon or that there's iron or silicon or whatever is on there. And like I said, for us, for the purposes of this lecture series, we're going to talk about how these atomic spectra kind of poked people to start thinking about the electronic structure of an atom a little bit more. Right, so now we've talked about how light is sort of strange and it has properties like diffraction. That proved to be really useful for the whole field of atomic spectroscopy. And it was odd, right, that there are only these specific wavelengths for specific elements that get absorbed or emitted. And they're always the same for hydrogen. They're always the same for all the samples of sodium or all the samples of carbon. And that was really interesting. And so in the next video, we're going to talk about this concept of quantized energy levels and move into the Bohr model, right? Because that's really the next step. As people thought, well, these gaps between the wavelengths of light must have something to do with the electronic structure of the atoms. So that's what we're going to talk about in our next video. So hopefully you have a little better idea of what these atomic absorption and emission spectra are, why diffraction is important. You put them through a prism so we can break up the different kinds of light, and then what might it be used for. So keep an eye out for the next video. Keep studying. Good luck.